Chapter 13 is a nice add-on to Chapter 12, extending some of the basic capital budgeting topics. In Chapter 13, we'll briefly cover the topics on the slide: timing option, abandonment and shutdown options, growth options, and flexibility options. We'll also look at optimal capital budgets and capital rationing. Capital budgeting, as we've covered it so far, is basically static. The assumption is that if a project is accepted, it'll be pursued exactly as defined. No changes made once it starts. The real world doesn't work that way. The potential to improve or even abandon a project can impact the NPV. Real option analysis allows us to investigate the impact of midstream changes. While the actual application of true real option analysis is beyond this course, we can take an overall look at what it involves. Real options involve anything that can be done before or during the project's life to reduce risk or improve profit. Investment timing options could involve starting with a pilot project before committing major funding, or delaying a project start to obtain better market data. Abandonment, contraction, or temporary suspension are all options to reduce risk. Expansion options could involve adding new items, new products, new markets. Flexibility. Consider a BMW plant in South Carolina designed so that the production line can be easily shifted from sedans to convertibles. First, let's look at a timing option. Project X cost $100,000 and expected to produce after-tax cash flows of $33,500 for the next 4 years. With a cost of capital of 10%, the NPV, $61.90.49. It's a go. However, if the company waits a year, they'll have more information about market conditions and the impact on the project's expected after-tax cash flows. Based on that information, there's a 50% chance of a strong market, 50% chance of weak. Strong market would produce cash flows of $43,500 a year, weak market $23,500. Note that the $100,000 will only be invested if the prospects look strong. Should we do it? Putting the 50-50 probabilities into a timeline. A strong market will result in an NPV of $37,889. Weak market, minus $25,508. The firm should not go forward. Recall that the $100,000 is invested at time 1, not time 0. So the expected NPV at time 1 of waiting is $18,944.57. Taking that back to time 0, $17,222.34. Clearly, the firm should wait to invest. The value of the option to wait is the NPV we just found minus the original NPV, $61.90.49, or $1131.85. An additional issue is the role of volatility. Increased volatility in the possible outcomes increases the value of an option. Consider if the strong cash flows are $53.5, the weak estimate $13.5. And there's our timeline. Now the expected value at time 1, $34,794, discounted back to time 0, $31,631. That's a lot. Contrasted to the original value of $17,222 is obviously added value of higher volatility. On timing options. Delaying does push cash flows further in the future. It might be better to just go ahead if there are advantages to being first to market, but waiting, as we saw in our example, may let a firm take advantage of more information or changing conditions. Without going in depth into the numerical analysis of real options, let's look at a simple abandonment example. Our new project Y has an initial cost of $200,000, cost of capital 10%, expected cash flows for 3 years, $80,000 a year. Straightforward NPV, a minus $1,051.84. It's a no-go. Suppose, however, that we believe there is a 60% probability that customer acceptance will be very good, generating cash flows of $150,000 a year. However, there's a 40% chance of poor acceptance, negative $25,000 a year. Here's the revised dual path timeline with the cash flows and probabilities shown. Again, straightforward NPV analysis yields an NPV of $173,027.80 for the top leg, minus $262,171.30 for the lower leg. Applying the 60-40 probabilities, same as under the single path timeline. Suppose further that the company does not have the option to delay the project, but they can abandon it after the first year if customer acceptance is poor. Then there'd be no cash flows after that. The further revised dual path timeline reflects abandoning the project after year 1 on the lower leg. Upper leg NPV still is 173, but the lower leg changes to minus 222. The addition of the option to abandon has turned this project from an NPV of a minus 1051 to a positive NPV 14,725.77. Since the abandonment option reduces risk, it could also reduce the cost of capital, further improving the NPV. Now let's consider a growth option. GRE's project has a cost of $3 million. Again, the outcome probabilities are 50-50. 50% chance of cash flows of $1.5 million for 3 years, 50% chance of $1.1 million, 12% cost of capital, NPV 122.38. Here's the growth option. If conditions are positive, GRE has the option to invest an additional $1 million at time 2. This investment would generate an additional $5 million in cash flows for year 3. Again, using the 50-50 probabilities, the revised NPV is 1503 or $1.5 million. The value of the growth option is the difference between the two calculated NPVs, 1380.85. Flexibility. We aren't going to look at any numbers associated with flexibility options as they become quite complicated. Flexibility basically considers the value of investing today to have more flexibility in the future. 2 examples are noted in the text. When BMW built a plant in South Carolina, they designed the production line so it would be easier to change from building coupes to convertibles based on consumer demand. Florida Power and Light made extra investments to allow them to easily change between oil and natural gas as a power source. Basic finance theory says that the value of a firm is maximized when the marginal returns exactly equal the marginal costs. So how does this play out in a firm? The CFO estimates the firm's cost of capital using retained earnings. We already know that once retained earnings are exhausted, the cost of equity as well as the cost of debt and preferred will rise. For our examples, we'll assume the cost of capital applies to all divisions. Each division then evaluates all proposed projects and reports the IRR for each, and they're plotted on a graph. The division IRRs are plotted highest to lowest, the dotted line. The solid line is the firm's cost of capital. Note the increase when the firm has to go outside for additional funds. The optimal capital budget is the intersection of the 2 lines. From this graph, it appears that it is in the firm's best interest to go outside for additional funding. All projects to the right, downside of the dotted line, will not be funded. Our last topic, capital rationing. Capital rationing can be termed soft, meaning that the firm has decided that they'll not invest more than a specific amount for the year. Perhaps the market is not good, they don't want to go outside for funding, regardless of how attractive the projects are. Remember, projects are not inherently good or bad. It depends on the cost of money. Hard capital rationing implies that the firm has exhausted all sources of capital. For our example, the firm has 4 projects with the dollars invested and NPV shown. Note that projects B and C are mutually exclusive. This table explores all the combinations of the 4 projects that the firm could undertake. Remember that NPV is additive, so the NPV of investing in both A and B is the sum of the NPVs of the 2 projects. With an unconstrained budget, A, B, and D is the optimal budget, highest NPV. If the budget is constrained to $10 million, then A, C, and D is the optimal choice. $7 million constraint, A and D is optimal. This ends Chapter 13 and this course.